Okay, so we should be recording now. So welcome everybody to the second lecture of these aspects of high energy physics course. In last lecture, we spoke a bit about the theory underneath high energy physics. And we quickly went over some aspects of the standard model of particles and fields. I hope you could get the link to the reference, and the lecture slides themselves are also posted in the same page. Unfortunately, there was a technical mistake yesterday, and I thought I had managed to record to the cloud the lecture, and turns out that I didn't. I'm sorry for that. So this time I'm recording on my computer, so now it should work. And then let's see if maybe I can just re-record it just for you, and then it will be available in the YouTube channel of the organizers of the school. So sorry about that, but this time it should work. Okay, so for the second lecture, I'm going to start speaking about the experimental aspects of high energy physics. So how do we actually collide these particles and how do we detect them? So I'm going to talk about these two things, particle accelerators and particle detectors. I'm going to speak a little bit more about the detectors because particle accelerators is really the field of a kind of a different breed of physicists, accelerator physicists. The design of detectors is something that high energy physicists themselves do, but accelerator physics is something a bit on the side. But anyway, we have to speak a bit about it. So, accelerators. In slide number 2, you can come with the obvious question. Why accelerators? So, namely, why do you want to accelerate particles to high energies and to do high energy collisions in order to study subatomic physics, high energy physics, but at this point, it's kind of a circular argument. So why is subatomic physics high energy physics? And the answer is that with larger energy, we have these two effects here. First, we know from quantum mechanics that h μ is equal to the energy. We usually see that as h bar omega, but it's the same. So with higher energies, we have higher frequencies, and higher frequencies means smaller wavelengths. So with higher energies, we can explore smaller distances. And this is not at all unlike what you have in solid state physics. Remember, in solid state physics, if you want to study a crystalline network, you would have to investigate it with a radiation of the same wavelength, so photons of the same wavelength, as the interspacing of the crystalline network. And usually that's X-rays. So here is more or less the same idea. You can explore smaller distance if you go to higher energies. So we can go and look inside the proton. The second thing comes from relativity. Remember, E equals to mc squared. What does this mean? This means that if you have enough energy, you can produce new particles. And you can see this kind of stuff, for instance, from Feynman diagrams, right? So if you have some process, I'm drawing here, something like quark-quark, so a quark collision. So let's put a gluon here instead of a photon. It again can give rise, for instance, to a pair of top quarks, which are much more massive than the original quarks. And where does this extra mass come from? It comes from the energy of the original parts. So high energy collisions open up through special relativity to quantum field theory the possibility of creating new massive particles that usually don't exist in natural conditions. So if we want to study all these particles, we need these high energy collisions. And then the question becomes, okay, I'm convinced that we need higher energies. How do we get them? Accelerators, but it's not as easy as, sure, let's just add an accelerating device. What does that even mean? So I'm going to try to give you some information about this. In slide number 3, we first have to come to terms to a fundamental split in the design of colliders. Either we're talking particle collider properties or we're talking fixed target experiments. What's the difference? In a collider, you're usually colliding two particle beams, one against the other, like in the bottom here of this picture in the right. For fixed target, you usually have one beam and you collide it against a solid material, or maybe even a thin film, but bottom line against a macroscopic object. So in a sense, it's easier to set up a fixed target experiment. What's the catch? Let's calculate the total relativistic energy available, okay? So you make this calculation here, assuming the two particles that are colliding. And then you say that one of them is a beam particle B, and you say that it's colliding with a fixed target particle A. And then you run the numbers here, and turns out that the total relativistic energy available for the collision goes only with the square root of the energy of the particle beam. Because remember, you have to go to the center of mass frame of the collision in order to make these calculations in an easy way. And turns out that you will have this relation here, which is not exactly good, right? I mean, you're losing most of the energy you put into the beam. On the other hand, it's trivial that if you have two beam particles, and let's say that they are identical at this point, then you run the numbers again, and you come to the obvious result that the total energy is twice the energy of the beam. So hooray, let's always do colliders. What's the catch? First, it's obviously much harder to aim two particle beams at each other than aiming a single beam at a macroscopic object. So it's a technically more challenging experiment. And second, there is the fact that obviously a macroscopic object is much more dense than a beam bunch in a collider experiment. If you run the numbers, let's say that you're colliding protons against iron. Solid iron has something like 9 × 10⁻28 atoms per cubic meter. The LHC beam bunch, on the other hand, is much, much, much more thin. Sure, it has 10⁻11 protons, fine. But 10⁻11 is nothing, essentially, compared to something like Avogadro's number, right? So if you run the numbers, the density of protons in an LHC beam bunch comes out to be 1 proton per square meter. Sure, the beam bunches are extremely, extremely small, something like a few centimeters of length and a few microns of width. But still, 10⁻11 protons is not that much. So the bottom line is that, sure, you have much more energy available, But on the other hand, you have many more targets if you are colliding in a fixed target configuration. So you have to do a choice. For high energy physics, usually the need for high energy obviously dominates, and ever since we have had collider experiments. Now, with this in mind, in slide number 4, how do I accelerate particles? It's obvious, right? I mean, if they are charged, you might as well simply put a large difference of potential in there and just let the particles be accelerated by the electric field. That does work, but it has a limit. If you have these particles, say, in air, you usually wouldn't have them in air, but still. At some point, the difference of potential in between your two electrodes would be so large that you would just have an electric rupture, a lightning bolt in between the two electrodes, with all the unhealthy consequences that this entails. But in general, it's extremely hard to have very high difference of potentials. You can have some megavolts, but megavolts will only give you mega electron volts. And that's not enough. High energy physics has gone through mega electron volts, MeV, to GeV, to TeV now in the LHC. So you have to have some other kind of mechanism. I could give you the whole history of accelerators here, but instead I'm just going to talk about what's used right now. I invite you to look at the history of particle accelerators, and it's a very beautiful history, including the famous accelerator at USP, Electron, but we don't have time for that. Instead, I'm going to talk about what's used right now. Let's start with linear accelerators. So the key thing is that in linear accelerators, you have these elements here called radio frequency cavities. And the idea is that you have an oscillating electromagnetic wave trapped inside here. You know how this goes. You have solved this problem in your electromagnetism course. The point is that you have these waves going back and forth. And if you do it right, you have particles coming in here, riding the wave, quote unquote, in such a way that the particle is accelerated in a half period. But then the wave comes back, right? It does, because it has to be a standing wave there. So if we don't protect the particles from that, we want to be able to accelerate anything. So the idea is that when the breaking half period of the wave comes by, the particle enters this region here, which has a conductor, such that in this small region here, it's essentially field free. So when the wave is going on the other direction, the particle doesn't feel it. And then the particle gets out just in time for it to be accelerated again. And so on and so forth. Now, of course, the particle is being accelerated. So that means that the time that it has to stay inside these drift up regions has to be larger and larger. But of course, you design it for that, and you run the whole cavity at some well-defined frequency, such that, and you synchronize everything, such that the things turn out, work out. This works, and this is the state of the art. This is literally what's used at LHC right now. And then what's the key? The key is that you have plenty of these guys, one after the other, and the particles get pushed from one to the other, getting more and more energy. What's the problem? First,
Thiago,
yes?
I'm sorry. This frequency is just the de Broglie frequency of the electron or
No,
proton?
no, it has nothing to do with that.
Okay, so I didn't understand very
okay,
well.
so let's do the following. I will ask to save the questions until the end. If you can put them here in the chat, then we can have a session of discussing at the end. Thanks.
Okay, okay.
So the problem here is that the energy here will be limited only by the accelerator length. Of course, you can put more and more of these resonant cavities one after the other. Of course, you are limited on space. And of course, you can only add so much energy at each step. And you hit diminishing returns because remember, even though you add more and more energy, which is fine, but the speed has a limit, which is the speed of light. So you don't, of course, you cannot get around it. There is one more thing that after you do the collision, imagine that there is another beam coming here and colliding in here. Then after the collision, boom, the beam is lost, right? It's not like this beam can do something on the other side because the cavities on the other side are pushing on the other direction, so it doesn't work. But of course, it's obvious what we're going to do. We're going to do circular accelerators, so more on that soon. Here, let me quickly tell you about circular accelerators. Again, there are many different kinds of circular accelerators. The cyclotron, the synchrocyclotron, and what exists these days, which are essentially synchrotrons. All circular accelerators nowadays, they are synchrotrons. And the key thing is that you have to synchronize the particle velocity, the electric field for the accelerating cavity, and magnetic fields that simply bend the particle so they make it curve, such that you can make the particles go round and round and round, going through the same accelerating elements again and again and again. Now, I will ask people to please mute when they're not speaking. Thanks. So you have to synchronize these two things, and of course, synchronizing the electric field and the magnetic field. Sorry, synchronizing the electric field and the particle velocity is just what I had said before. However, you also have to synchronize the magnetic field that does the bending, because you know that the bending power and the curve that the particles make is related to the momentum of the particle. And when you do that, you want your particles to keep in orbit. So the momentum changes. And so the magnetic field that you need to keep them in orbit also changes. And all of this has to be synchronized together. I'll give a bit more details about all the elements here later. Now, one thing that you have to think about, okay, but what particles do we want to collide? Well, this is all based on electromagnetic fields, right? So the particles have to be charged. On top of that, they of course have to be stable because they have to survive for a macroscopic amount of time in order to feel these many pushes as they go round and round the collider. And this already is a tough order, right? Because what particles we have? Protons that fit these two needs. Protons, electrons, and they're antiparticles, right? Antiprotons and antielectrons. Sure, you can have pion beams, but you cannot really accelerate them. You can accelerate them a little bit, but eventually the pions will decay. There are talks of making a muon collider, but again, you have the same problem. Muons, even though they are fairly stable and they can live for almost macroscopic amount of time, eventually they decay. But there are people studying to see if it's possible to do. So in the end, you either have proton or electron colliders. And then you hit a conundrum. If you want to have actual proton and electron, so either a proton-proton or electron-proton collider, you have the problem that you need different magnets for the different types of particles. Why is that? Because, well, if it's both protons, sure, the particle, their masses and their charges are exactly the same, but they have to go in opposite directions. So you need one magnet to bend them on the clockwise direction and one magnet to bend them on the anti-clockwise direction. For electron and proton, you don't have this problem. The same magnet will naturally bend them on opposite directions. So one will go clockwise and the other will go anti-clockwise. But then they have different masses, so you have a different need for bending power. So you need different magnets anyway. But then it's easy, right? Just let's use particle-antiparticle. So proton-antiproton or electron-positron. Fine. Then you can get away with just using one set of magnets in one vacuum tube. But then you have this uncomfortable problem that antiprotons and positrons are antiparticles. And it's not like they are so easy to get. How do you get them? So positrons are more or less easy to get because you can get them from some fairly easy reactions like a laser shining on material. You shine a laser on a sheet of metal or something like that, and if you get the right setup, you can get this reaction here: electron photon going to electron positron electron. Antiprotons, however, are a bit hard because the way to get them, you actually have to do a nuclear physics experiment, collide a proton with a nucleus, and hope to get antiprotons out of the reaction, capture them, and get them in a beam. Here, a picture in the top right, it's a picture of the then working, but now has been deactivated, Fermilab Accelerator. The Fermilab Accelerator is actually the one on top, and it's larger, but there's perspective in the picture. And this one in the bottom is the main injector, which injected the protons and antiprotons into the Fermilab Accelerator, which was named the Tevatron. Why Tevatron? Because it accelerated particles to 1 TeV. Okay, so more on these elements. So how do you actually make these radio frequency cavities? Usually they are made from niobium, which is something that's in the news lately, as you know. But the thing is that they are extremely hard piece of both mechanical and electronical engineering. And right now, we are getting to the level that these radio frequency cavities, they will have to be such well constructed and well tuned as to get an accelerating power or equivalently field strength of 35 megavolts per meter. And if you make the calculation that, oh, I wanted to accelerate my electrons to, let's say, 500 GeV, you can divide one thing by the other and see that this international linear collider will actually have to be a line of a few kilometers. I'll let you do the calculation. I won't do it. Then, on top of that, you also need the magnets, and this is yet another problem. Let's focus on just two kinds of magnets. First, you need dipoles. Why dipoles? Because if dipoles, you can easily bend the particles and make them curve. And if you run again the numbers for what kind of field strength do you need to bend particles that are traveling at, let's say, 500 GeV or 1 TeV or 7 TeV, like in the LHC energy, turns out that you need the magnets at the level of a few Tesla. And if again you remember your electromagnetism classes, you will notice that a Tesla is an extremely strong magnetic field. And this immediately brings us to the problem on how to get these kinds of fields. The answer is superconducting electromagnets. So in the LHC, we have these dipoles which are 14 meters long, which are superconducting. So they are kept at 1.9 Kelvin. How do we get this temperature? We get a lot of liquid helium. And since they are superconducting, we can get very high currents from them, and keep them circulating in the magnets without they dissipating anything, because in a superconducting magnet there is no resistance. And again, you can run the calculation here of the bending power, and you can ask yourself, okay, if I want to make to bend a proton that's traveling at 7 TeV energy with this kind of field, what's the bending radius? And from that, you can get the minimum ring circumference, because you have the radius of curvature, and from there you can get the circumference. And the answer is the 27 kilometers of the LHC, of course. And that's one of the technological problems that accelerators face. We cannot get much stronger fields, and therefore we have to have large curvature radii, which means large accelerators. The problem with large accelerators, as you can imagine, is that they are expensive. There are many other kinds of magnets in the LHC for focusing and so on and so forth. This is all the studies that you do in your usually your second electromagnetism course, the one where you essentially work in optics of charged beams. But I just want to draw your attention to the focusing. So if you look here at the quadrupole, if you remember, the quadrupole, if you have a beam that's going, a beam that's going on the, one second, how do I write like this? If you have a beam that's going in the Z direction here, you know that there is a force that pushes it to the center in one of the axes, but away from the center in the other. And you know that there is a theorem that it's impossible to have it to have a magnetic configuration such that it's always pushed down to the center. So you use the quadrupoles to focus, but you know that if you focus in one of the axes, you defocus on the other. So the answer is something that's called the Photon cell, where you have a pair of quadrupoles that are twisted 90 degrees with respect one to the other. So first you focus in one dimension and defocus on the other, and vice versa on the other cell, on the other part that is the defocuser. And you hope that overall, you don't hope to design for it, that overall the effect is focusing the beam in the center. And allow me to say that the dynamics of charge of relativistic charged beams is a really complicated area. And actually, in my personal opinion, these are the people that are doing the best job at CERN and at the accelerators everywhere. So much kudos to them. I'm happy that they exist, but I don't want to delve into their territory too much. Here are just some nice pictures for you to see. So this in slide number 7 on the left is one of these radio frequency cavities. This is made of niobium. Here in top right is one of the LHC dipoles being lowered to the LHC itself, so 14 meters. And here on the bottom right, this is a quadrupole, yes. For a second, I thought it was an octopole, but it's actually a quadrupole. And you can see here the four poles. I'm not going to zoom in because it's going to screw up the sharing, but you can see that there are 2 holes here, C1 and 1. And the key is that you need one for each beam. Remember, the LHC collides proton beams. So in this, you see here that you have 1, 2, 3, and 4 poles, which then again correspond to the 4 poles that that we just discussed here. So in slide number 8, when I said synchrotron, it should have dawned on some of you the word synchrotron radiation. And when I said accelerator, some of you should have noticed that we have an actual state-of-the-art accelerator here in Brazil. You know that I'm talking about Chile in Campinas. So, synchrotron radiation, you know what it is, right? If you have a charged particles bent travel in a circle, you can calculate how much energy they lose to Bremsstrahlung. And it's this formula here. And this m, namely this m to the 4th, 1 over m to the 4th, is our bane, because this means that for light particles, we lose a lot of energy. So for electrons, we lose a lot of energy to Bremsstrahlung. And we don't want to do that. Remember, we want to accelerate the particles. So for us, it's a problem. Particularly for an electron-positron machine, it turns out that there is a more or less soft limit that the beams will have to be around 100 GeV per beam. For an accelerator of reasonable size, something like 20 kilometers or so. And 100 GeV was good enough for the Lepton large electron-positron collider LEP that run in the 90s at CERN. But for higher energy machines like the Tevatron and the LHC, you simply cannot get there, at least not with the technology we have now. So these are Hadron colliders, essentially proton or proton-antiproton colliders. The good thing is that then we have synchrotron radiation under control. The problem is that, as we discussed in the previous lectures, hadrons are bound states of quarks and gluons, and they are completely messy. We have to do all those calculations about parton density function, underlying event, parton shower, hadronization. Electron collisions are clean. Electron goes in, electron goes out. Of course, synchrotron radiation is actually useful in its own right, and that's what the people in Campinas are doing, right? Because from this, you can get high energy photons with a very well-defined energy, which is good. It's like an X-ray machine on steroids. So you can use that to do amazing material studies. So for solid state physics and studies of biological compounds, taking pictures of the coronavirus, everything. So synchrotron radiation is an asset, but for our purposes of high energy physics, it's a liability. Okay, so in slide number 9, I quickly show to you the CERN accelerator complex. Let me quickly go through this. All these accelerators were, when they were designed and built, they were state of the art. So the first proton synchrotron was here constructed in 1959. And it has 628 meters of circumference. But eventually, as the need for higher energies appeared, the super proton synchrotron was constructed in 1976 with 7 kilometers of circumference. And the key thing is that turns out that it's a much simpler thing for an accelerator to work on a limited range of energies. It's easier to first accelerate, say, from 0 to 50 GeV, and then have another accelerator do the job of, say, 50 to 200, than trying to have one accelerator that goes from 0 to 200. This is, of course, related to the fact that as the particle accelerates, the radio frequency cavity and the magnets have to be synchronized in completely different range. So what happened, what was done in the CERN accelerator complex was that the proton synchrotron became a pre-accelerator that then passes the protons on and antiprotons to the superproton synchrotron to do a second round of acceleration. And at the time that the SPS was state of the art, it ended there. Of course, then the LHC came online in 2018 with 27 kilometers of circumference, and the SPS itself became a pre-accelerator to the LHC. You may notice that just like in any laboratory of the sort, there are also a lot of beam lines that are separate experiments on their own right. And these accelerators, the proton synchrotron and super proton synchrotron, give different beams at different energies to these experiments as well. CERN is not only the Large Hadron Collider. I just want to draw your attention to a last fact here, that we also have a decelerator that decelerates the particles, so pulls them down in order to do antimatter studies. So it's the same principle, but kind of in reverse. Another tidbit of information that I want to share with you is that the tunnel for the LHC is exactly the same tunnel as was built in the 80s for the Large Electron-Positron Collider. So I wish I had a picture of the LHC here, but I think it wouldn't do it justice. So you know you have seen countless pictures of the LHC in the internet and on videos, but the real thing is truly marvelous. So I will share with you a video later. Of course, I cannot put the video in the PDF. Okay, so let's make a break here. Suppose we accelerate the particles, we accelerate the protons, and we accelerate them to high energy and we collide them. Fine, what happens then? Many particles come out. Which particles come out depend on chance. Remember, it's a quantum mechanical process with the probability of a given final state being calculated with the bracket calculation that you know how to do from quantum mechanics and actually in this particular case, quantum field theory. How do we actually know what happened? And the answer is that you have to detect the particles that came out of the collision. And this actually is the half of the problem, the second part of the talk about detectors, that we are more interested in. So first, you have to detect the particles. They have to exist for a reasonable amount of time. And this already eliminates most of the particles that exist. Most of the particles that exist, either elementary particles or bound states, they are unstable and decay very rapidly. So they have to exist long enough to fly and to reach or whatever instrument we're using to detect them. And turns out that there are not that many. So protons, electrons, photons, and neutrinos are stable. The neutrino are hard interacts. It interacts only through the weak interaction. Neutrons, muons, long-lived kaons, pions, and charged kaons, they all live for at least 10 nanoseconds, which is enough for them to fly more or less 3 meters. And essentially, this is it. Of all the particles, either elementary or composite that we know, we only detect 4 plus 5, 10 if you take the 2 states here. But the neutrino hard interacts, we only detect 9 of them. So it's a tough call. How do we detect these particles? First, let's do the division. First, you have charged particles versus neutral particles. So charged particles, you can interact with them, you can detect them through their interaction, electromagnetic interaction, and hadrons versus everything else. Hadrons interact with the strong interaction, the nuclear interaction, and the others don't. So electromagnetic and strong interaction, essentially. But Thiago, what is all the other particles? And the answer is, you have to reconstruct them from the particles you detect. For instance, if you want to detect a Z, you don't detect the Z, you detect the decay products of the Z. And same for the top quark. You get the decay products. And reconstructing what actually happened in the collision is yet another story that we're going to talk about tomorrow. But the particles that we detect are essentially only this 9. So how do you detect? Well, clearly you have to make them interact with something, with bulk matter. You have to have a detector, which is a macroscopic object that they interact and somehow leave some kind of macroscopic signal that we physicists can see, measure, and understand. And these are going to be always electric or light signals. To reconstruct the particles from these electric or light signals is a different problem, and we'll talk about this on the next slide. So let's go through this. How do you detect a charged particle? Let's think first about charged heavy particles, stuff like protons and muons. Imagine a particle going through bulk matter, so solid state matter, so a crystalline network. How does this charged particle interact? And the answer is it collides with atoms. And by atoms, I essentially mean the electrosphere of this bulk matter, interaction of the electrons in the atoms. It mainly excites and ionizes these atoms. And then you run an amazingly lengthy calculation that we're not going to go through. But in the end, you have something called the Bethe-Bloch formula, which depends here on the Lorentz factor of the interacting particle. And with this classical electron radius here. Because remember, the particle itself is interacting with the electrons. And this is amazingly complicated. I'm not going to derive this here for us, but I'm going to do something different. I'm going to plot it. And here in slide number 12, if you look at the plot, you see something like this. This is the dEdx curve of the energy loss of heavy charged particles in bulk material. And you see that it depends, or it's easiest to plot in terms of this gamma beta product. So it's really the relativistic gamma and the relativistic beta, but since beta converges to 1. And then if you look at this, for instance, this is muons on copper. So how much energy muons lose on copper as a function of the muon momentum, or equivalently of the beta gamma product of the muon. And then you see that for this region between 0.1 and 1000, so sort of high energy muons, this is a good description, and there are 3 regions here. It starts high, then it reaches this minimum, and this minimum is actually very shallow. You see that you're very close to the minimum for an amazing range, something like 1 to more or less 50, or even less than 1. And these are the so-called minimum ionizing particles. And this is a good approximation. Charged particles that mainly interact electromagnetically, they interact in a way that they deposit a minimum of energy, which is enough to ionize atoms in the bulk material. And then you get a logarithmic rise here, and at very high energies, you have a plateau. But then at very high energies, you have a new process, which is these radiative effects here. And these radiative effects, they are reached only at extremely high energies for muons. But in slide number 13, I'm going to show you the other case, which is the energy loss for charged light particles, which is electrons and positrons. Electrons and positrons reach this radiation regime much earlier. And the answer is that as the electron and positron move in the material, not only they lose energy by ionizing the rest of the ionosphere, but they fill the ionosphere, sorry, in the electrosphere. They ionize the electrons in the atoms, but they also lose energy because they are moving through an electric field. And obviously they're accelerated. So bottom line, they do bremsstrahlung. So in addition to this bed block loss, which is more or less approximated by this collision term here, you also have the radiation loss, which is essentially effects from bremsstrahlung. And if you compare the two things, for instance, from the bed block formula, turns out that the ionization loss, they decrease logarithmically with energy, but they increase linearly with the Z of the material. The bremsstrahlung, on the other hand, it increases linearly with energy and goes quadratically with Z. So when you run all the numbers, it turns out that for high energies, and high energy with respect to what? With respect to the mass of the particle that is undergoing energy loss. Bremsstrahlung becomes the dominant process. And you can see here the two plots. Bremsstrahlung goes like this in red, ionization goes like this in blue. It's subtly different for electrons and positons, but it doesn't matter. There are other processes at very high energies, but they are not that relevant. And you see here that there is a critical point in which ionization starts losing out to bremsstrahlung. For electrons, this is more or less well described by this formula here for solids, for loss of energy of an electron going through a solid or through a gas. But for 1 GeV electrons, so relativistic electrons, bremsstrahlung is already essentially all of it. But Thiago, you were talking about muons. For muons, it's the same. But for muons, this critical energy is something around the 1 tera-electron volt, 1,000 times more. So it doesn't really come into play until the energies of the LHC. It's really hard to produce TeV muons. But at the LHC, where you are colliding 70 eV beams, every once in a while you get muons with an energy of 1 TeV. So they are relativistic muons, and all of these also applies to them. Let's delve a little bit deeper to this, okay? Let's assume that we are only talking about bremsstrahlung, because high energies, you only care about bremsstrahlung. Again, if you run the calculations on the bremsstrahlung, and here I'm not going to do it, you can open a book and see some semi-empirical derivation of it. You get this complicated formula here, where you have here the quadratic dependence with Z. There is stuff like the density of the material, the Avogadro number, the fine structure constant, stuff. But pay attention to this. It's proportional to the energy itself, as we had said previously. And if you undo the constants here, including the classical radius of the electron here, in the end you get this, okay? You get something like proportional to the energy over the mass square. And this again, why for the electron, it's much more important than for the muon. The electron is 200 something times lighter than the muon. But then you know what happens here, right? Because you can rewrite this previous expression this big thing here, like this, and this x0 is this complicated expression here. But now this is easy, right? This is a simple equation, and you integrate it, and you get this loss of energy, which is exponential. And this x0, if you do the dimensional analysis, is something that has a dimension of length. So this x0 is called the radiation length. So it's the distance in which the energy of the particle is reduced by 1/e. So more or less 1/3, because of the bremsstrahlung. But now you may think in slide number 15, Thiago, but bremsstrahlung, are you saying that more or less at every 1/x, every x0 length? Sorry, this was supposed to be an electron. At every x0, the electron will more or less emit a photon, emit some radiation, and lose 1/e, close to 1/3 of its energy. Kind of like that. And you will see what this leads to later. On the other hand, there are also photons, right? Photons, either photons that come from the collision or these photons that I just spoke about, they may or may not be important for your measurement. So how do these photons interact with bulk material? And again, you know the answer. You have done your lab, your modern physics lab. You know that there is stuff like photoelectric effect, where a photon ionizes an atom, and then you have this formula here for the energy of the electron that comes out. And if you, again, run the calculation, you have this cross-section for the photon interaction. Then you have Compton scattering, where it's more or less the same, but the photon survives. And you again know from your quantum mechanics that it has this formula here. So for high energy photons, again, doing some approximations, you end up with this particular expression here. And you see here the plot of the theoretical cross-sections and experimental points. Sure, it's not perfect, but fine. And you see here, you remember this from your lab, from your modern physics lab, right? These edge effects. And last but not least, you have at the highest energies, you have the pair production, which is the thing that at very high energy, a photon can interact with an electromagnetic field, either from a nucleus or another electron, let's say a nucleus, and it may convert. It may become a pair of electron positron, like this. And why is this dominant for high energy? Because this photon has to have at least the energy to produce the rest mass of the two electrons. Then, of course, it has to have the momentum, and of course, it has a momentum such that energy momentum is also conserved. Notice that if you try to impose energy momentum conservation and say that a photon by itself decays, quote unquote, becomes an electron positron pair, if you try to impose energy momentum conservation on this process, and remembering that the photon has zero mass, turns out that it's impossible. You really need the photon to be in an external field for this process to be possible. Because these other fields furnishes the rest of the balance for the energy momentum equation. And notice that the calculation, I'm showing it here with the Feynman diagram, is very close. It has a symmetry with the interaction of the electron with an external field. So we know how to do this calculation. And turns out that this is the dominant way that photons interact for photons with more or less above 1 megaelectron volt. And because of this symmetry, when you do this calculation, turns out that the cross-section of pair production comes out to be this expression. Fine, you do it. But it can be put in this form here, which again has the x0, the interaction length, the same one that we defined here, right? In this expression. Again, because of the symmetry in between the processes. This symmetry, of course, has a mathematical definition, but just notice that these diagrams are the same, just flipped 90 degrees. So, of course, a photon interacting with an external field and giving 2 electrons has a relationship with an electron interacting with an external field and emitting a photon in the Bremsstrahlung process. And turns out again that this more or less correlates to a simplified picture where a photon moves close to an interaction length and then splits into an electron-positron pair. It's approximated, but it's a good approximation. It's a good, not even a good approximation, but a good cartoon of what happens. Now, how do I clear like this? You can put these two things together, and at high energies, turns out that if photons are losing their energy through pair production, interacting with the field of the nucleus, and electrons, positrons are producing more photons through Bremsstrahlung process when they interact with a nucleus, turns out that these two processes can cross-fit each other. So if you rescale everything in terms of how much we're moving the material in terms of interaction length and how much energy is still available in the system in terms of the critical energy that's just defined for the electrons to still undergo Bremsstrahlung, you can get the situation where a photon decays after one radiation length splits into an electron positron, and each of those give rise to yet another photon, and then the photons do another pair production and more Bremsstrahlung and so on, and the energy gets diluted. And what's happening here is an electromagnetic shower, where, and it's, of course, it doesn't matter what's the initial particle. If it's a photon here, it will just, sorry, if it's an electron here in the beginning, it will just start with a Bremsstrahlung instead. But an electron or a photon may hit bulk material, and through a combination of pair production and Bremsstrahlung, if it's high energy, it will lose most of its energy in the material through these processes, until eventually the other processes come up and just ionize or do photoelectrical effect. But in the end, all of the energy is deposited in the form of an electromagnetic shower in the system, in the bulk material. Here you see a simulation of I just call this lead glass, okay? Of an electron hitting a piece of lead glass. This was done for the CMS experiment, the simulation. Okay, so much for electromagnetic interactions. What about the other side? What about the interactions of hadrons with matter? Interaction of hadrons is much more complicated because unlike electromagnetic interactions, our model of hadronic interactions is not as well developed. It's not like I can do quantum electrodynamics and do the explicit calculations that I showed you before. I'm just going to give you some rough pointers and tell you that a hadron, when it interacts with a nucleus through the strong interaction, it can either be an elastic interaction or an inelastic interaction. And these are, of course, when either the two parts come out intact, so proton nucleus going to proton nucleus, or not. And the elastic interaction is something like 10 millibarns of cross-section. The inelastic is much larger. You can see here as a function of the center of mass energy of the system, the total cross-section of proton-proton and the elastic cross-section. And you see that the elastic here is much smaller. At high energies, there's also something called diffraction, but I'm not going to talk about it. And it turns out that with some approximation, the inelastic cross-section goes up with something like the atomic number to the 2/3 power. So if you run these numbers, the total cross-section of a proton with a nucleus is something like the total cross-section of a proton with a proton times this factor here. And then what kind of interaction is that? First, it's something here in slide number 19. But before this, let me tell you that it's something like a hard sphere interaction. Remember, the hadronic interaction is much unlike the electromagnetic interaction goes with 1/r, right? The potential. The hadronic interaction is much more strict. When you are out of the nucleus, it decays exponentially. So to some approximation, you can treat it as if it were a hard sphere interaction. The calculations are more involved and are semi-empirical, but in the end, you can do the same game that you can define a hadronic interaction length, which is this lambda interaction here, which has this particular form here, which turns out to be proportional to the A to the 1/3, where again, A is the atomic number. And this characterizes both how deep a hadron can get inside a material and how wide this shower goes. Remember, let me show you here quickly that I should have said this before. I'm sorry if I go back here to slide 17, that there is both a depth and a width that characterize the electromagnetic shower. And both of these are going to be more or less related. Similarly here in slide 19 for the hadronic case, the interaction length will characterize both the depth and the width, so the longitudinal and the transverse profile. The difference here is that instead of the energy, here you do it in terms of the number of particles in the shower. So again, the same calculation, it's a simple differential equation, you solve it, and you get this. And now notice that the radiation length, if you remember, it went to something like 8/z². While the interaction length went like this. While the radiation length, yes, I know that the names are a bit unwieldy, but that's what it is, goes with 8 to the 1/3. So if you divide one by the other, it turns out to be 8 to the 4/3, which for essentially everything that is not hydrogen. So, but from essentially every material, turns out that the interaction length, the interaction length is much harder than the radiation length. What does this mean? That means that to stop protons, to stop hadrons, you need much more material than you need to stop electrons and photons. You can put this in terms even of let's call it radiation protection. If you want to protect yourself from beta radiation, so electrons, mostly a piece of paper will do, right? On the other hand, if you want to protect yourself from alpha radiation, you need tons of lead and concrete. But for our purpose, that means that, and I'm already going to tell you here, you use this kind of stuff to use these kinds of interactions to measure the energy of particles in what's called calorimeters. If you want a calorimeter to measure the energy of hadrons, it needs to be much larger than a calorimeter to measure the energy of electrons and photons. And here you have some comparisons of the interaction length and of the radiation length for different materials. And you can see here that always the interaction length is larger than the radiation length. Okay, so now we know hadronic interactions and we know electromagnetic interactions. We know how these particles interact with bulk material. What do we do with it? Remember, we want the particles to deposit their energy and give us some kind of signal that we can detect, measure, and do some kind of analysis with it. So let's talk about how do we use these interactions to build real detectors. Let's start with something called scintillators. Scintillators are materials that through whatever interaction, a particle deposits its energy on it, and it converts it into light, into, in the end, a bunch of photons. So electromagnetic interaction has to be involved because there's photons in the end. But the point is that photons are light, so you collect it with a photosensor. The details of this is usually based on the process called fluorescence. So the idea is that in the material you have energy levels, and an excited electron moves from a higher to a lower energy level. The key thing for a good scintillator is that it has to be transparent to its own fluorescent light. So, for instance, if the scintillator shines in blue, you want it such that blue light can go through it. Why? Because you want the light produced in your scintillator to actually go through it and hit some kind of photosensor here on the other side. Of course, the conversion must be efficient. You want enough of the energy to be transformed into photons such that this becomes an actual reasonable amount of light to be detected here. And this light has to be at some kind of a frequency that we can build photosensors, photomultipliers to detect it. What does the photomultiplier do? Again, it's a particle detector that detects these photons that at the end produce electrons, and these electrons have to be collected in such a way that it becomes some kind of macroscopic charge that's moving. Macroscopic charge that's moving, electricity, signal, done. You measure it. So that's the key. So scintillators are essentially at the base of many detectors in high energy physics nowadays. You use them in this configuration that I just told you to build the particle counters, the stuff that just counts the presence of radiation there. Image displays. So you can imagine that you have an array of scintillators, and you use them to measure, and you have some kind of, what's the name of that? Position sensitive detector, such that you can essentially image the radiation that's coming to you. You can, depending on the relationship of the light that the scintillator produces and the energy of the particle that is hitting it, you can use it to make energy measurements, and you can use it to make trackers, which are specialized position sensitive detectors that track the passage of charged particles. I'll talk more about these trackers later. I'm just going to tell you there are three types of scintillators, essentially, that can be used. Each one has its advantages and disadvantages. They can be inorganic scintillators, liquid noble gas scintillators, and these are the usual materials that you hear about, for instance, in the liquid argon calorimeters, and organic scintillators. I have to go a bit faster, but if you want more details about the physics and the usage of scintillators, and again, there are examples of these at your local university, I'm pretty sure, you can either contact me offline or search for the reference that I gave you. Another kind of detector that uses the interactions that we just spoke about are gas chambers. And gas chambers, they're based on the ionization of a gas. How does this work? You get a charged particle that passes through a gas and interacts with it and ionizes it. It's either a single gas or, but more commonly, a gas mixture. And ionizing it just means that the electron and the ion are separated. So the key thing is that you put an electric field here. So you have a cathode, you have an anode, and the ion and the electron have opposite charges, and then they move and they induce an electric charge, sorry, an electric current, which you measure measure electric current, signal, bing, you're done. And the key thing is that in a gas chamber, depending on how much field you apply to it, you can run it on many different regimes. So you can see here on the right, this plot of the number of ions collected as function of the voltage. And you see here that you can have an avalanche of ions and electrons in the sense that ions and electrons are again charged particles going through the gas. So they can ionize even more and so on and so forth. Just like the showers we spoke before, but not in the sense that it's just the electrons and photons doing, these are much lower energy regime, but the idea is the same. These are the so-called delta electrons, secondary ionization electrons. And then what can happen is that the ions and the electrons can recombine. And then at low voltage, this happens a lot, so you don't collect many ions. Then at some level, you have a constant number of more or less constant number, let me annotate here, a more or less constant number of ions collected. Then, and this is what's called a gas chamber running as an ionization chamber. You can increase the voltage and you can have a system where the number of ions collected is more or less proportional to the voltage that you apply. But at some time, even this breaks down. And again, you hit another plateau, but at a much higher level. And this is the regime that the gas chambers are used in the Geiger-Miller counters. And at some point, you just break the dielectric because applied too much field. And all of these depends on the diffusion of electrons and ions through the gas, the mobility of the charge, and the details of the avalanche process. But the key thing is that the gas chamber, depending on the admixture of gases and the voltage that you apply and the geometry, let me go back one slide, and the geometry here, it is an extremely flexible detector. Another kind of detector is the so-called semiconductor detector. And it is more or less like the gas chamber, but different, and you will see how. The key thing with semiconductor detectors is that unlike gas detectors, they are radiation damage resistant. And why is that good? Because remember, when you are doing a particle collision, lots of particles come out. And these particles are in a very real sense radiation. So sure, your detector is here trying to detect them, but the detector is being hit by these Hadrons particles and eventually may degrade. And it's the kind of thing that we see in the experiments. Of course, this radiation goes with 1/r², just because if you're far away, you're being hit by less particles. So, but if you want to be really, really close to where the collision happens, that means that you need to have some kind of radiation resistant detector. And this is good because this exists. We have silicon detectors. And even better is that since there is this whole industry of semiconductor machining, obviously for microchips, we can produce semiconductor detector is even a few microns of precision. But of course, this has a price, and in this case, it's a literal price because silicon wafers are expensive. Here I show you a picture of the CMS pixel detector, which is a gigantic silicon detector composed of silicon pixels that are sensitive to the passage of charged particles and can pinpoint the detection and can track and pinpoint the detection of charged particles with a precision of a few microns. So how does this work? It's more or less the same idea. Charged particle passes and it will produce electron-hole pairs. And then these electron-hole pairs will more or less behave on the same way as the electron-ion pairs in the gas detector. That's why I said they are similar. But of course, there is a difference that here is a crystalline material, and then you have to play that game with the energy bands. Remember your solid state lectures? Yes, it's that. So we're going to have to talk about the conduction band, the valence band, and the energy band, and the energy gap. And it's exactly what I have here in slide 25. In an insulator, you know, there is a valence band and a conduction band, and the Fermi level is in between the two. So the point is that in an insulator at the ordinary temperatures, the electrons cannot reach the conduction band. And then they cannot go, quote unquote, free to conduct electricity. So this is an insulator. In semiconductors, though, the band gap is small enough such that thermal energy can bridge this gap. Just the thermal fluctuations can make electrons jump a bit. Of course, in a conductor, the two things overlap, and then you have your regular conductor, just like a metal. But in this, the key thing is that in the semiconductor case, this gap is very small. So just with the thermal fluctuations, they can make the jump. And again, as you know from your solid state lectures, the key thing is to dope the semiconductor to already create some kinds of holes or extra electrons to make this bridging of the gap and therefore the improvement of the detection capabilities easier. So you know these, there are N-type or P-type doped semiconductors. I'm going to use just silicon from now on, okay? Of course, there's other stuff like germanium, but silicon is the thing we all use because again, silicon is already used in the industry. So you can dope the semiconductor, adding a material like antimony that contributes 3 extra electrons, or you can dope it with, let's say, boron, and then it's missing an electron, and then you have an extra hole. And both of these help improve the conducting. And then you know what to do, right? You do a p-n junction, you put the N-type material in contact with the P-type material. Those guys, the hole and the electron find each other, and you create the depletion region, and this completely change the semiconductor conductivity. And then you play the game that you apply an external voltage. You connect the cathode to the P-type, the anode to the N-type, and this makes the depletion zone larger. And the current across the junction becomes very, very small. And then there is no signal. And then that's the situation that we want. Because then, in slide 28, when a charged particle actually goes through the detector, and now the depletion region is big, it will go through, it will generate a lot of electron-hole pairs, and then they'll drift, and then we'll get a signal. But now, remember, we control the size, because we control the depletion region size, because we control this external voltage here. So for instance, here you have a silicon detector that has microstrips. So they are strips that are short in one dimension, or something around some tens or hundreds of microns, and then they're long in the other direction. So the charged particle goes through. You have a diffusion velocity, which is a function of the electric field, which is a function of the electric potential, and you have some mobility, which depends on if you're talking about the electron or the hole. The electron or the hole, the electron and the hole, they are very similar, just a factor of 2 difference. It's completely distinct from the gases. And then you have the mobility as a function of energy, as a function of the electric field here, which is either constant, goes with 1 over the square root, or 1 of the field. And then you run the same calculations, trying to calculate the mean time between collisions, which depends on the mean free path of the material. And eventually the drift velocity saturates at something like 10 to the 7 centimeters per microsecond. But again, this depends on the mobility, and the mobility depends on the field strength. So one of the things that you can do with all these handles is try to achieve a constant drift speed, drift velocity, because then you can determine drift time, because it's constant, and you can measure it. So you can have a lot of information. You can have, assume that these are the microstrips here, okay? So this is a microstrip, this is a microstrip. You can see where the particle went through in this axis, for instance, by seeing which charge is measured in this and this and all the other microstrips. And then you can kind of make a barycenter of the measurement. And then you can measure the drift time and get information about these axes as well. And remember, all these particles here, all of these structures here, they have some microns or tens or hundreds of microns of size. So you can do this in a very, very, very precise manner. Gas chambers, for comparison, they are usually they usually have the size of some centimeters. So these are much more precise. But Thiago, this is done because if silicon detectors are so much better, why don't we have silicon detectors everywhere? And the answer is the same answer as why don't we have the best everywhere, right? It's obviously because silicon detectors are much more expensive than just taking a big chamber and filling it with gas. Let me go a bit quicker. One of the things that is particularly important for silicon detectors is that with the V drift, which is, if I go back here for a second, it's something like 10 to the 7 centimeters per microsecond. Turns out that you start seeing the charge moving in your detector very fast. The rise time, this time here, there you see the induced charge in your electrodes. It's something on the order of 1 nanosecond, which is very fast. So that means that you can have, let's go back to schedule 28, a lot of particles coming through very fast, and you will be able to see the signal of them all. Sorry, Of course, there are details that sometimes you are in a situation where the mobility is not constant. Sometimes the charge goes where it shouldn't go, or it's distributed over a surface, so this measurement is not perfect. But overall and all, silicon detectors are extremely superior with respect to gas detectors. But of course, they are much more difficult to build, and because of that, much more expensive. Okay, so Thiago, all of these detectors, what do you do with them? And the answer is that you kind of build full systems that I'm going to just divide into two categories of systems: trackers and calorimeters. And the key thing is that the idea of trackers is to measure the charged particle tracks in a non-destructive way. So what's the thing? You have some kind of medium that will produce signals as the particles pass through it. So maybe a gas detector, maybe a silicon detector, maybe a scintillator, doesn't matter. And you put everything on a magnetic field. And then what this will do is that this will bend the particles, and you know that bending the particles, there is a curvature radius that if you can measure, you can get the momentum of this particle. And if you build your detector right, the particle may go through many layers of this detector. And then you can have multiple measurements that you can use to try to reconstruct this curvature radius. And then there are these two types that I have alluded to already: semiconductor trackers, which you can use for high particle rates. So you can put them closer to the interaction point. They are more expensive. And gas trackers, which you can use for lower particle rates, say far away, and they are cheaper. Of course, there is other possibilities. You can, in principle, have also something based on scintillators, and there is a lot of R&D being done here. Or you can build a calorimeter. A calorimeter here, instead, you want to use those showers that I spoke before, either the electromagnetic or the hadronic, to measure the energy of charged particles or of neutral particles. This is the key thing that the calorimeter can do for you. Because remember, to do in the silicon detector and in the gas chamber, you need a charged particle to go through, ionize, or make electron-hole pair and measure. But the calorimeter can measure the energy through the shower of neutral particles, either the photon or the neutron hadrons, like the neutrons and chems. So the key thing here is that here it showers and it destroys the particle, totally absorb it. So you need two things. You need dense material, because then the particles will interact a lot. Remember in those expressions that the density of the bulk material was there as an explicit factor. And you need something active to either shine or produce a measurement, an electric measurement of some sort. These two materials may not need to be the same. So you can have what's called a sampling calorimeter, where you have layers of something to absorb and something to detect. Or you can have a homogeneous calorimeter where you have one material that plays the two roles. So here, these are just some cartoons, but the idea is the same. Again, I can show you later some pictures or actual videos of how this looks in real life. There were some pictures before, sorry. The key thing is that you can imagine that this is a silicon tracker, and these are the activated spots where the charged particle went passed through. Then from these charged spots, from these activated spots, you can try to do some kind of fit, as you can imagine. and measure the curvature radius, and from here the momentum. Here on the center, you have the scheme of a sampling calorimeter where you have an absorber layer where the particle showers, and then you measure its energy on an active layer. For instance, this can be something simple like a brass or copper or iron. And then here for the active layer, you have some kind of scintillator. And then you alternate them. And then you can make very, very complicated structures that optimize the measurement, like was done, for instance, in the Atlas liquid argon calorimeter, where you have this accordion structure here, which is filled with liquid argon. And it was a success. The Atlas calorimeter is extremely good. Okay, I am almost running out of time. So let's quickly go to the end. And now we integrate all of it together. We want to study the collision. We want to measure the energy, the momentum, ideally even the charge, the mass of all the particles produced in the collision. What's the plan? First, take the non-destructive measurements before the destructive measurements, obviously. So try to observe the passage of the particle and don't disturb it too much. So use materials that have small interaction radiation lengths. Track it, put it in a magnetic field, and measure its momentum. Then make it undergo a shower in some kind of bulk material in a calorimeter and measure the energy. Measure the energy, measure the momentum, measure the charge, because you know if it's turning clockwise or anti-clockwise, then you can have a pretty good idea of what kind of particle it is. There are two cases which are different, okay? Muons. Muons penetrate a lot in bulk material. They have very high range. You need something like 12 meters of pure copper to stop a 20 GeV muon. So it's very hard to measure the energy of muons. So an alternative is to build calorimeters that let the muon pass through, because it will pass through, that are reasonable in size, so less than 12 meters of pure copper, and then add another tracker at the end. And then the idea is that the calorimeters will stop everything but the muons. And then you know that whatever reaches the end is muons. The second special case is the neutrinos. Neutrinos interact only through the weak interaction. They are neutral leptons, so they're leptons. They don't interact through hadronic interactions. They are neutral, so they don't interact through electromagnetic interactions. So they have very small cross sections. They are almost ghosts. Every second, zillions of neutrinos go through the Earth, go through your body, and you don't even notice. So to detect neutrinos, you really need dedicated experiments that detect neutrinos, stuff like Kamiokande, Mini-Boon, and Jayme. With these caveats, you build the multi-purpose detectors. So here you have a slides. This is a cross-section of the CNS experiment, and the idea is that it's divided into layers, like an onion. The first layer is a silicon tracker, and then you track all the charged particles like muons, electrons, and charged hadrons. You have a calorimeter which has very low radiation length, and that system stops electrons and photons. The hadron calorimeter stops all the hadrons, including neutral hadrons, as well as charged hadrons like pions and protons, and neutrons and kaons. In CMS, everything is inside a big superconducting solenoid, so the charged particles bend. You could have it such that the solenoid is just here around the silicon tracker, but because of the physics of a solenoid, it's better to have it with a large bore, with a large hole inside. And then you have another tracker and only muons, usually only muons survive until here, and then you track the muons again here. And because of the return field of the solenoid, the muons here go in the other direction. And with this, you measure all the particles. You measure their energy, you measure their momentum, you know their charge. You should now know what's happening in their collision. Just quickly talk about the tools of the trade. If you want to simulate all of these, GEANT4 is your friend. It's a toolkit to simulate the passage of particles to matter. We use it in high energy physics, but not only. You use it only, for instance, in medical applications, because you can use it to simulate the stuff like hadron therapy and PET scans, and also in space science, because in space radiation is a big problem. And that's something called Delphis, which is a framework specialized on simulating these detectors used in high energy physics. And with this, I finish my lecture. Thank you very much. Next lecture, now that we detected the particles, we have to actually reconstruct the data, interpret the signals that our detectors give us, and see and try to make some physics out of it. Thank you very much. I am quickly going to go through the questions in chat. I saw two questions. First is if the slides are going to be available. Yes, they are going to be available. They should be on the same website of the school itself, of the Jayme school of this year. And wow, if you say that you're trying to learn PN junction, the class is helping you so much. I'm glad to hear that. And but I'm pretty sure that there are much better explanations around, okay? And there is a second question that was the one that was before, the source of the beam frequency, if not the de Broglie frequency of the particle. Let me go back to that. It's the question that we had before. And coming back, I think it's should be.
Could you go to the
here.
slide where I think it's previous to this, where we see the length of the path of the beam? And you said that
The length of the path
yes,
of the
yes,
beam.
yes.
This one. Yes.
Yes. The drift tubes.
Ah, okay, yes, I remember now. No, it has nothing to do with the de Broglie frequency. The de Broglie frequency is an intrinsic frequency of the electron related to its quantum mechanic properties, something about the wave matter duality, blah. No, it has nothing to do with that. For this, you don't even need to think about the electrons as quantum mechanic objects. It's much simpler than that. You really want to synchronize the frequency of the radial cavity, so the frequency of the electromagnetic wave that is traveling here, with the fact that when the frequency is in the wrong direction, so when the wave is traveling such that it would break the electron instead of accelerating it has to be protected inside the drift tubes, so it doesn't feel it. When it comes back just in time for the wave to go in the other direction. The frequency of this wave, electromagnetic wave that is here, depends only on the geometry of the cavity and on the frequency that I'm driving it. So you have that's why it's a radio frequency cavity. You set up the geometry of the cavity, you set up a driving source, and then that's it. It's literally just the frequency of the driving oscillator.
But when we see the proton source as an electromagnetic wave, this is a quantum mechanical interpretation.
The
right,
proton source as an electromagnetic wave, I don't follow what you mean. The electromagnetic wave in here is nothing to do with protons or anything like that. It's literally that problem that you solved in your electromagnetism course. The one that you have a barrel and you have a wave in here. And you remember this, right? You have to solve the best functions, all the harmonic. It's literally
confined
just
waves.
That. Exactly, confined waves. It's literally just that. And then it has the natural frequencies, remember? But then you can add an oscillator that drives this, and then the problem becomes something like a forced oscillator. And then the key thing is that you have to synchronize this frequency of this confined wave such that when the electromagnetic wave that's traveling here is going in the wrong direction, the electron is protected inside the drift tube where it doesn't feel the breaking field. It's much simpler than what we were thinking.
Yes. And these drift tubes, what are they made of to protect the proton, the beam?
They are made of it's a conductor tube, but it's done in such a way, in such a geometry that inside the field is zero. It's again just it's probably niobium again, okay? I don't know the details.
Yes.
But it's just the geometry problem of having an electromagnetic geometry problem of having a field-free part of the space.
Okay, it's clear now.
Yes, sir.
Thank you.
Sure.
Yes, sir. Rafaela Martins asking for, do you know speak Portuguese?
Não, eu falo português. Claro que eu falo português.
Então, caramba, aí, ó, Rafaela Martins, ele fala português, cara.
Não, mas me pediram para dar o talk em inglês. Eu estou seguindo o que o pessoal da escola falou.
Ah, então tá certo que você tinha um sotaque assim, então eu falei, pô, ele fala português, ou ele é muito polonês lá das terras indígenas do meio do mundo, e ele tem um sotaque estranho. Daí eu fiquei confuso, mas a Rafaela
desculpa, professor, eu achei que você só falasse inglês. Foi mal.
Não tem problemas. But again, I'm going to speak in English just for the fact that there may be students from abroad, okay? There are 100 people here, and there may be some colleagues of ours that don't understand Portuguese. So, but again, if you come and you want to talk to me, you should have my mail. It's on the webpage of the school. Feel free to come to contact me. Let's chat, let's discuss. I love talking to students.
Thank you.
Cheers.
Eu não tenho inglês muito fluente, mas muito obrigado aí, eu tô já indo.
Perfect. Any other questions?
Professor, os slides você vai enviar por e-mail? Você sabe também onde que estão colocando as aulas gravadas?
Então, a primeira aula não foi gravada porque eu errei, tá? Eu achei que eu estava salvando na nuvem. Descobri que a nuvem não existe. Então, a primeira aula a gente perdeu. Eu vou tentar gravar uma de novo e colocar lá. Agora...
Mas eu lembro que você apertou para gravar, eu lembro.
Sim, eu também lembro. O problema, como eu falei, foi para a nuvem. E, aparentemente ficou na nuvem, eu não consigo tirar da nuvem.
Ah, entendi.
Enfim, mas essa aqui deve estar gravada no meu computador e eu vou falar com o pessoal da escola para subir para algum outro lugar.
Beleza. Então tá bom. E sobre os slides é por e-mail mesmo?
Deveria estar no website, que é esse website aqui. Deixa eu ver.
Aqui eu tô...
Aqui, olha, aqui no Zoom eu vou tentar colocar. Vão aparecer aí, esse é o plano.
Ah, eu tentei pegar esse link e eu não consegui. Obrigado. Muito obrigada. Muito bom. Obrigado, professor.
Eu que agradeço. Okay, so if there are any other questions? Okay, so we stop the recording now.